Welcome back to It Is Funny practice. Same formula as before, but they're starting to talk more about cells and giving us a little less information, so we have to use skills from previous lessons a little bit. Okay, they're talking about a magnesium chloride electrolytic cell, which is going to start with magnesium ions and chloride ions. If you're electrolyzing these, you're going to be converting the magnesium ions into metal and the chloride ions into chlorine. That would mean this side's releasing electrons, this side's gaining electrons. That's probably enough to get this problem done. They say what's deposited at the cathode, that's where the reduction is happening, so that's the magnesium reaction. I guess they say magnesium, but if they just said determine the mass of product deposited at the cathode or something, you might have to figure out that the cathode is where the magnesium reaction is occurring. So, can forget about the chlorine, doesn't matter for this. And they tell us, let's get an inventory of information. They say the current is 10 amps. They say the time is 2 hours, which is 7,200 seconds. You go times 60 to get to minutes, and then times 60 again to get to seconds. And, of course, we know the Faraday constant. It's the same number every time. So we can find our number of moles of electrons. That would be IT over F. Because we divide both sides by F in the original formula. So current, 10 times time, 7,200, divided by 96,500 is the Faraday constant. And we get 0.7461 moles of electrons. Now, according to this, it takes 2 electrons to make 1 magnesium. So, however many electrons you have, you divide by 2 to get the amount of magnesium. If we take this number and divide it by 2, divide that by 2, and you get 0.3731 moles of magnesium. If you don't like the divided by 2 thing, the more rigorous explanation for this is we're multiplying by 1 magnesium, because that's what you get here, for every 2 electrons that you put in. Multiplying by 1 over 2 is the same as dividing by 2. So, there's our moles of magnesium, and the mass of magnesium will be number of moles times molar mass, meaning 0.3731, times 24.31 is the molar mass of magnesium, and from that we get 9.06901 grams of magnesium. 3 sig digs, Faraday constant has 3, so we can give this answer to 3 digits, 9.06, and then because this number is 5 or more, we round up and we say 9.07. Easy. Lots of work, but hopefully easy. If not, don't worry, we have 1,000 more practice problems. The firm wishes to plate 10 grams of copper onto baby shoes from a copper nitrate solution. If a 2 amp current is used, calculate the time required. Okay. Well, our formula requires moles of electrons, and they've given us moles of copper indirectly. We can start with this. Moles of copper will be the mass of copper divided by the molar mass of copper. That's 10 grams divided by, is it 63.55? Yes. Molar mass of copper is 63.55. 10 divided by 63.55 is 0.1574. That's probably enough moles of copper. They tell us this is a copper 2 solution, so the half reaction we're getting is copper 2 turning into copper metal. Not surprisingly, that means 2 electrons. So to make a single copper costs 2 electrons. To make this much copper costs 2 times this electrons. That's 0.3148 moles of electrons, and now we finally have a number we can put into our formula. Formula starts at IT equals Fe. We're trying to find time, so divide both sides by I, and we get time equals Faraday constant times moles of electrons divided by current. So 96,500 is the Faraday constant times 0.3148 divided by current is 2 amps. And we get a time of 15,189 seconds. Divide that by 60, you get like 253 minutes. Divide by 60 again, and you get 4.2, let's see, 3 sig digs, so 4.22. It comes out 4.219 on my calculator, but when you round that, you get 4.22 hours. So a little over 4 hours to do the plating. And they say, at what electrode should the shoes be attached? This reaction is oxidation or reduction? The copper is going from +2 down to 0. That makes it a reduction. Reduction has a letter C in it, so from that you could say it must be happening at the cathode. The other way to think of this is when you have a power supply, power supplies have a positive terminal and a negative terminal. The negative terminal is negative because it's full of electrons, and it pumps out electrons into whatever it touches. So if you have a reaction that uses electrons like this, you would want to connect it to the negative terminal, so it'll get fed a constant stream of electrons. If you have a reaction like chlorine turning into Cl2 plus electrons, a reaction that produces electrons like they're a waste product, you have to clear away these electrons, and so this you would want to connect to the positive terminal. Positive terminals are positive because they're electron deficient, they're poor in electrons, and so they will suck in electrons from anywhere else. So a reaction like this, an oxidation reaction, you want to connect to the positive because it will absorb the electrons you're making. A reaction like this that requires electrons, you connect to the negative terminal because it will provide the electrons you need. That's comfortable. If any of this is not, please follow up with your instructor and they can go over it with you or answer any questions you have, hopefully. Okay, so we're making fluorine today. It's a scary day at the office. And we're starting with 80 grams of fluorine gas that we intend to make. The number of moles of fluorine that we're talking about is mass divided by molar mass. 80 divided by, fluorine's molar mass is 19 per atom, but it's 38 for F2, which is what fluorine gas really is. 80 divided by 38 is 2.1053 moles of fluorine. But our formula wants moles of electrons, so we have a bit of work to do. The reaction that makes fluorine is at the very top of the table, and we're doing it in reverse. It's 2 fluoride ions turning into fluorine gas and releasing 2 electrons. The important part of this is 1:2 ratio. It takes 2 electrons to make 1 fluorine. So if you want this much fluorine, multiply that by 2. It takes 2 electrons to make 1 fluorine, and we get 4.2106, if my brain math is correct, moles of electrons. Okay, so how much current does that mean? Formula starts out IT equals FNE. If we want current, we want I alone, divide both sides by T, and we get current equals Faraday constant times moles of electrons divided by time. So 96,500 for the Faraday constant times 4.2106 moles of electrons. The time is, I should have done this in advance, sorry. 10 hours times 60 to get to minutes times 60 again to get to seconds. It's going to be like 36,000 seconds. And from that I get a current of 11.287 amperes. Everything we've been given had 3 significant digits, so we can cut this to 3 digits and we get 11.2, but wait, this is 5 or more, so round up. 11.3 amps. What electrode will this happen at? We have F minus turning into F2, so the charge is going from -1 up to 0. Charge going up, or oxidation state goes up, means it's an oxidation. Oxidation has an A in it, so it happens at the anode. Or think of it as the positive terminal, because we need something to suck up these electrons that we're producing. And finally, for this page at least, calculate the current required to plate out 35 grams of nickel. I'll go a little faster because you've seen this before. 35.0 grams of nickel. Molar mass is, I just did it, I did it instead, 5869. Molar mass of nickel is 58.69 grams per mole. Divide that and get 0.59635 moles of nickel metal. But our formula wants moles of electrons. Again, this is nickel 2, so the reaction looks like nickel 2 plus 2 electrons turns into nickel. Ratio is 2 to 1. So it costs 2 electrons to make a single nickel atom, then multiplying that by 2, and I'm never getting that done in my head. We need 1.1927 moles of electrons. And our formula, this is the standard way to start it. They want us to find current, so we want I alone, so divide both sides by T, and we get current equals Faraday constant times moles of electrons divided by the available time. So Faraday constant's 96,500 times moles of electrons, found them up here, 1.1927, divided by, they did it again, 10 hours, so 10 times 60 times 60 is 36,000 seconds. And we get a required current of 3.197 amps. Everything here was given at 3 significant digits, so we can trim our answer to 3, and that would make it 3.20 amps. Good? Hopefully good.